The Gaussian function, e to the negative x squared. It looks fairly simple, yet it has wide-reaching applications all the way from statistics to quantum physics. So what if we want to integrate it? Well, that turns out to be surprisingly difficult. If you've never heard of this before, then this might sound odd. After all, we know the antiderivatives of e to the x and negative x squared, so their composition can't be too bad, can it? Well, actually, e to the negative x squared has no elementary antiderivative. No matter what substitution you make, whichever way you try to apply integration by parts, and however much time you spend on it, you'll come up with nothing. Luckily though, there is a trick for evaluating the definite integral of this function from negative infinity to positive infinity. We start by multiplying the integral by itself, so we're dealing with the square of the integral. We can now change the variable in the second integral to y, because obviously changing the letter won't change the value of a definite integral, so long as we also change the dx to a dy. And now we see we have something we can write as a double integral. The double integral over all of r squared of e to the minus x squared times e to the minus y squared dx dy. E to the minus x squared times e to the minus y squared can just be written as e to the minus x squared plus y squared. This is now in a form that we can turn into a polar integral. The x squared plus y squared becomes r squared, and we multiply the integrand by r, the Jacobian. Now to change the limits of integration. We are integrating over the entirety of r squared. The way we can express this in terms of r and theta is putting theta from 0 to 2 pi and r from 0 to infinity. Finally, we have something we can actually integrate. The integral of r e to the minus r squared is minus a half e to the minus r squared, and with the bounds from 0 to infinity, this is equal to just a half. So now we have to work out the integral of a half d theta from 0 to 2 pi, which is quite clearly just pi. But we're not quite done yet. Remember, this is the square of our original integral, not the integral itself. If we look at the Gaussian function, we see it is quite clearly positive everywhere, so its integral is the positive square root of pi. Since e to the negative x squared is an even function, we know that its integral from negative infinity to 0 is equal to its integral from 0 to positive infinity, and the sum of these integrals is the one we've just worked out, root pi, so each one must be root pi over 2. But this doesn't give us a way to work out an integral with any bounds we like. We still don't know what, for instance, the integral of e to the minus x squared from 0 to 1 is. Now, at the start of the video I said that e to the negative x squared has no elementary antiderivative, but it does have a non-elementary antiderivative. Let's take the Taylor series for e to the x. It's the sum from n equals 0 up to infinity of x to the n over n factorial. To get a power series for the Gaussian function e to the negative x squared, we can simply substitute in negative x squared for every x. So we end up with the sum from n equals 0 to infinity of negative 1 to the n x to the 2n over n factorial. Now we have something we can integrate. When integrating this with respect to x, we can take the integral inside of the infinite sum, and take the negative 1 to the n over n factorial outside of the integral, since that's just a constant with respect to x. The final answer is the sum from n equals 0 to infinity of minus 1 to the n x to the 2n plus 1 over 2n plus 1 n factorial, plus the constant of integration. This power series has an infinite radius of convergence, although I'm not going to prove that here. Here is a graph of it with the constant of integration set to 0. So now let's work out the integral from 0 to 1. To do this, we simply take the power series evaluated at x equals 1 and subtract the power series evaluated at x equals 0. Notice that every term in the power series evaluated at 1 has 1 to some power, which does nothing, so we can remove it. Notice also that every term in the power series evaluated at x equals 0 has 0 to a positive power, so it is just an infinite sum of zeros, which is 0. So now we're just left with the sum from n equals 0 to infinity of minus 1 to the n over 2n plus 1 n factorial. Of course, we can't evaluate this exactly, but we can add up enough terms to get a good decimal approximation. The sum of the first 5 terms gives us 0.74749 to 5 decimal places. The sum of the first 10 terms gives us 0.74682 to 5 decimal places. The sum of the first 50 also gives us 0.74682, so we can be confident that this is what it converges to. So there you have it. The integral from 0 to 1 of e to the negative x squared is just under 3/4. The true answer is irrational, so we have to make do with the decimal approximation. Okay, that's everything.